This is my entry for the 2017 Moog Circuit Bending Challenge. The main goal of this project was to create a drum machine, but instead of lots and lots of dials, I'd have dots that I can move around the screen using a Nintendo Zapper. There are 4 channels and up to 16 steps. I'm going to show you how I control a step right now. I hit this button, which is controlling a 4046 VCO, point again at the screen. Now I can move the dots around. I can adjust the speed of the sequence using this knob. Using these buttons, I can have the sequencer skip certain steps. So I point the gun at the screen, I push the delete button, and now it's going to skip over the bar that I had the gun pointed at. These knobs here are a mixer, which let me control the volume of each channel. This is the main volume. This is the power control, just off and on. This is the control for the 4046 VCO. It's got 2 settings, high and low. It's just select different capacitors for the oscillator. This channel controls the first tape deck. This one runs very slowly, so it's a very deep ambient type of sound. This button lets me control the second tape deck. This one's got a much faster speed, so I like to use it to cause distortions to self-help tapes. This button lets me control a circuit bent spelling toy. So it can be set to either do the alphabet or animal noises. I'm going to turn to animal right now. This button here selects which letter or animal noise it's making. Now I'm going to play with all 4 channels at once for a while. You're going to notice that if I want a sound to be off during a step, what I'll do is I'll move that bar all the way to the left side of the screen. That just makes it turn off. So the Zapper needed some modifications. Normally it won't respond to just pointing at a white screen because Nintendo didn't want it to be easy to cheat at ducking up by pointing at a light bulb. But I fixed that by removing a 10 nanofarad capacitor. Then I found one of the transistors in it was really slow and bad, so I put a better one in there. And I also put some tape on the lens because when I use such a small TV, it's hard to point at the individual lines in the drum machine. So to build the case, the first thing I did was go to a scrap metal yard, and I found these metal panels that already have holes cut out of them, which for me is perfect because all I have is a hacksaw. So I can just remove sections of this very easily and get a fairly nice looking metal panel. To build the sides and the base, I got a 2 centimeter thick shelving board. I cut out my design using a jigsaw. Then I stained and varnished it. The case was designed to open very easily. These are the batteries. It's 9 volts from 60 cells. This is here to keep them in place when the case is closed. It just comes down and lands on top of them. This is the tube, speaker, and circuit board from an old portable black and white CRT television. The Zapper only works with CRTs. This television, it didn't have any composite input, there was only an antenna. So I had to look at the circuit board and figure out where the demodulator was and then bypass that. The TV's tuning knob had this really interesting string and pulley indicator system, so I'm reusing that to show the tempo. On the back of that is a 555 A-stable circuit, so the speed of that gets set by a potentiometer, and every time it pulses, it advances the drum sequence. These are a pair of tape drive mechanisms from an old boombox. I've left the circuit board for reading the tape head on, but I've disconnected the motors from that, and now I'm controlling their speed directly with the drum sequencer. The tape drives had some heavy metal discs to give them inertia to spin smoothly. I took those off because that's not what I want. The buttons were all salvaged from an old keyboard. They're very nice and clicky. This is a 4046 VCO circuit, which makes some of the beeping noises. When I was building it, I found if I didn't connect the power wire, it would draw power through the VCO input and cause more of a distorted sound than the clean square waves they normally give. This is another 4046 voltage controlled oscillator, but this one is used to drive the clock of a chip on a children's spelling toy. So that will decide how fast the toy speaks. This is a rotary switch, which is selecting what the toy is going to say. These are outputs for headphones and an external TV. Here it is running with an external television. This is CRT as well, so I can also use it to do some control. So this board here is nothing but 4051 demultiplexers and capacitors. Each capacitor stores the position of one of the dots on the screen as an analog voltage, and the 4051s let me address that and draw them on the screen as well as send them to the sound outputs. This is a 5-volt regulator. The Zapper and a lot of the other parts in this project like to run off 5 volts. So these three chips are used to generate the composite video signal. This is a 4060, which is a binary counter that you can connect a crystal oscillator to. So I'm clocking that with a 20 megahertz crystal, and its purpose is to count up the timing as a horizontal scan line is drawn. Over here is a 4040, which is another binary counter, but this time without the oscillator built in. The purpose of this is to count up the number of scan lines that have been drawn to know when to restart drawing the screen. This is a 4059 inverter, and all of these are diodes, which I'm using for diode logic. I can't do inversions with diode logic, so I've got an inverter chip to do that, and all the AND and OR functions done with diodes. A composite video signal has synchronization pulses, and these periods called porching, and there shouldn't be any video going in. So the purpose of the logic is to have these events go off at the correct times. These components are used for getting the horizontal position of the light gun. Uh, these two transistors and capacitors form a sawtooth wave. This is a high-speed op-amp for buffering that sawtooth wave. And this is a 4066 quad analog switch, which is used to form a sample and hold circuit. This is another pair of 4040 binary counters. These ones are used to provide a count that goes from 0 to 16 during the course of drawing a frame of the composite video. Composite video signal has 240 lines, which you divide down into 16. So this first one here counts up to 15, and then it resets itself through diode logic. It gets incremented every time there's a single scan line. When that one resets, it triggers the second one to count. These are a pair of 164 shift registers. They're used to create a 16-bit circular shift register. Each bit of that circular buffer decides if the drum sequencer should play a step or skip past it. This is another 4040 binary counter. This one stores the present position of the drum sequence. It gets clocked by a little 555 circuit. The chip right below it is a 74LS85 4-bit binary magnitude comparator. So what this does is it compares the output from the drum step 4040 to the output of the counter that's going up by 16 as the screen is being drawn. And that lets me get a white line which highlights on the screen what step the drum sequencer is currently on. It also triggers a sample and hold circuit which takes the correct value out of the capacitor array through the 4051s and then out to the VCO circuits. These are both LM324 quad op amps, and this is a 4066 quad analog switch. These are used to form 4 sample and hold circuits which take the value out of the capacitor array and then give it to the voltage controlled oscillator circuits. This is an LM339 quad comparator. I'm using that to create a pair of window circuits. A window circuit outputs high when two voltages are close to equal. What I'm using that for is to generate the dots that are on the screen. What I'm doing is comparing the sawtooth wave that's tracking the horizontal position of the CRT raster beam to the voltages coming out of the capacitor array. These are 100K logarithmic potentiometers for the mixer. On the board below it is what lets me shut off a sound channel by moving a dot all the way to the left side of the screen. It uses a LM339 comparator and a 4066 quad analog switch. What it does is it checks if the control voltage is below a certain level, and if it is, it shuts off the returning audio because that goes through the 4066. Now I'm going to describe how the light gun drum sequencer works. There's links in the description to more complete circuit diagrams and stripboard pictures. Now CRT looks like a solid image, but there's actually a single raster beam going across it 60 times a second. It's moving in a pattern like this. The next two graphs represent the activity happening on a single scan line. A Nintendo Zapper is basically a phototransistor combined with some lenses. This circle represents where that is pointed on the TV. So if it's pointed at the center of the TV, there will be a pulse coming out of the zapper around the center of the scan line timing. If the gun is pointed on the right side, this pulse comes out later. It's on the left, comes out earlier. This is a circuit I'm using to generate a sawtooth wave. There's a pulse in a composite video signal called H-sync that goes off at the start of every scan line. I use that to discharge a capacitor through a 2N3904. Then I let that charge up slowly through a regulated 2N3906 circuit. That creates a wave that rises and then resets and back to zero and rises again every scan line. This is a buffer because the circuits coming after it could affect the voltage of the capacitor otherwise. Next, I add a 4066 analog switch IC. This just acts like a switch that closes when one of the input pins goes high. The trigger for this is the zapper, and what's going into it is the sawtooth. Then at the other end, what I add is a 1 microfarad capacitor to ground. So what's going to happen is if the zapper is on the left side of the screen, pulse goes off here, and the switch is only closed during this period, which means the voltage stored in the capacitor is going to be low, around 0 volts. The zapper is further over the side, the pulse goes off later. When the switch is closed, the voltage of the sawtooth is like this, so now the voltage stored in the capacitor goes higher, up to around 5 volts. Now instead of using a single capacitor, what I can do is I can add a demultiplexer. So this here is a 1 to 16 analog demultiplexer. It's actually made with a pair of 4051s, but I like to imagine these like rotary switches. So this is 4 bits as the address, and that decides where the switch points. If they're equal to 0 in binary, it points to 0. If they're equal to 8 in binary, it points to 8. If they're equal to 13 in binary, it points to 13. Now I can store this voltage I'm generating from the zapper pulse and the sawtooth in a different capacitor depending on this binary input. Next I use a 4040 binary counter chip to count from 0 to 15 as the scan lines are being drawn. So when the very first scan line is being drawn, it'll be at 0. Then when the very last one is being drawn, it'll be at 15. I run this binary count to the inputs of this demultiplexer. So now when the screen starts being drawn, it's at 0, and then it will just move up until the screen is finished being drawn, and then it resets and goes back to 0. So if the gun is pointed at the 8th line near the center, we sample the sawtooth in the center to get this voltage, and then that ends up being sent to capacitor 8 because the binary count controlling this demultiplexer will be at 8. If the gun is pointed all the way in the bottom left, the zapper pulse will go off here. The demultiplexer will be pointed to 15. So we sample the voltage here, then we send that out and store it in capacitor 15. This is a window circuit. A window circuit uses 2 comparators to check if one analog voltage is close to a second analog voltage. So what I'm doing is I'm using one input as the sawtooth and the other input as the capacitor multiplexer, so just either sides of that 4066 switch. It's going to see if the voltage that the capacitor that's presently being pointed at by the demultiplexer matches the voltage of the sawtooth. Because the sawtooth is going up as the screen is being drawn horizontally, this will produce a pulse at a different horizontal position based on what voltage is stored in the selected capacitor. This is what gets the little dots on the screen that indicate the values of each of those capacitors. Next I add another binary counter circuit. This one, the speed is controllable through a dial. As you turn the knob, it affects how fast a 555 oscillates, which affects how fast the 4040 counts. This is used to store the present position of the drum sequence. So it's got another output of 4 bits. This is a 74LS85 binary comparator. So it's got 2 inputs which each take 4 bits, and it has an output which goes to 1 whenever those 4 bits in either input are equal. One input is the 4 bits from the display count, and the other input are the 4 bits from the 4040 drum step count. So this will just create a pulse whenever the 4040 that's counting the drum steps matches the line of the sequence that's being drawn on the screen. Run that back out to the TV, and that's what gets the white line that highlights where the drum step count presently is on the TV. This is a sample and hold circuit. So what I do is I run the voltage coming out of the demultiplexer into that input, and then I control it with the output here of the 740 LS85 all the way around here. So what happens is, because the output of the binary comparator is only going to be 1 when the drum step matches what's on the screen, and what's on the screen matches where the demultiplexer points, it means the value stored in this capacitor is going to get set to whatever value is inside of the capacitor multiplexer array that matches the drum step count. If the drum step is at 2, then this switch is only going to be closed when the multiplexer is pointed at 2, which means that the value stored in this capacitor is going to be equal to the value stored in capacitor 2. So this is the final output of the system. It's just a control voltage, which I'm setting with the zapper, and then selecting based on the sequence from the drum step sequencer. And this runs out to some 4046 VCOs, and it's also used to control how fast some tape drive motors are running.
Much of that time spent in meetings is non-productive. Meetings often start late, or there's too much socializing or going on tangents and running overtime. See how meetings can waste time? Multiply the wasted minutes of your next meeting by the number of participants. For example, if you wasted 10 minutes and there were 12 people at the meeting, that would be a total of 120 minutes.